and gentlemen, welcome to webinar Difference Between Heat and Temperature.
I'm Amibia Rama and my partner Indah Jasmita Anwar, your master ceremony in this afternoon.
We would like to thank everyone here for taking time to attend our webinar today.
His Excellency Mr. Professor Dr. Enjung Kawai, our awesome speaker today.
Honorable the Dean Faculty of Science and Mathematics, Diponegoro University, Mrs. Professor Dr. Widowati.
Respectable the Chair of Physics Department, Professor Heri Sutanto, SSC MSc, and respectable all participants on this webinar. Okay, before we go to the next session, let's start by singing the national anthem Indonesia Raya.
Di Bandung, Indonesia, bangsaku, bangsa dan tanah airku. Indonesia bersatu, itulah rakyatku semuanya, Allah jiwanya, Allah badannya untuk Indonesia.
Ladies and gentlemen, let me recite the rules of this webinar. First, rename your account name with the name _ format when joining the Zoom room.
Second, participants are requested not to activate the microphone feature during the webinar activity.
Third, during the webinar, participants are required to activate the camera feature.
Next, attendance link will be sent via Zoom chatbook and certificate will be sent after you fill in the link. So please fill it carefully.
Fifth, participants can ask the research person in the Q&A session by using the Zoom chat box with the format name _ origin of the region _ instance or agency _ question, or raise your hand and activate the microphone feature.
Six, moderator have full right organize the webinar.
7. We will send the webinar material via email at the earliest on H+1 webinar. Ladies and gentlemen, first of all, thanks to God who has given us some mercies and blessings so that we can attend this webinar today without any troubles and obstacles.
Before we go to the next session, allow me to read today's agenda. The first agenda is opening with prayer. Secondly, speech by our Honorable. Third, presentation and explanation from speaker, and the last is closing. These are the today's agenda will be presented soon.
Ladies and gentlemen, let's open this agenda by praying. Praying begin. Amen. Pray enough. Thank you very much.
Moving into our second agenda, which is a speech from the chairman of Physics Department for Mr. Professor Dr. Heri Suntato, SSC MSc. Please welcome.
Thank you for Mrs. MC, Ms. Jasmita, and Ms. Rahma. Bismillahirrahmanirrahim. Our Honorable Visiting Professor, Professor Dr. Jun Kawai from Department of Material Science and Engineering, Kyoto University, Japan. Our Honorable Dean and Vice Dean, Faculty of Science and Mathematics, Diponegoro University, Senior Lecturer in Physics Department, Diponegoro University, and all participants of the webinar. Assalamualaikum warahmatullahi wabarakatuh. Ohayou gozaimasu. And good afternoon, audience. We are pleased to cordially welcome Professor Kawai and all participants to the visiting professor webinar organized by the Physics Department, the Faculty of Science and Mathematics, Diponegoro University, Indonesia. The Faculty of Science and Mathematics aim to support research and education development in basic and applied science. Several workshops and visiting professor programs have been implemented to promote Diponegoro University as world-class university. This webinar is the second webinar given by Professor Kawai in the Physics Department. Last year, Professor Kawai discussed about three-dimension printer spectrometer, and today Professor Kawai will present the difference between heat and temperature. Thank you, Sensei. We sincerely thank Professor Kawai for his attendance and significant contribution to promoting science and technology at Diponegoro University. We hope this webinar can inspire the student and lecturer in the Physics Department to improve their basic knowledge and gain a different perspective to understand physics. The webinar also proved that the cooperation between the Physics Department, Diponegoro University, and the Material Science and Engineering Department, Kyoto University, continues. Therefore, we actively support the extension of formal agreement between the two departments to prolong the scientific collaboration in the year ahead. Last but not least, please enjoy the webinar. And to close this speech, we officially open the webinar on the difference between heat and temperature. Thank you very much. Arigatou gozaimasu. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thanks, Mr. Heri, for giving a great welcoming speech for today.
Dear ladies and gentlemen, before we move to the next session, I would like to invite you to take pictures together. Please activate your camera feature.
Okay, please prepare yourself, Fabian. I will count until 3 and the comic will document it. Okay, be ready. 1, 2, 3. Okay, once again. 1, 2, 3. Okay, thank you very much, audience.
You're welcome. Yeah.
Ladies and gentlemen, move to the next agenda, which is presentation and explanation by our speaker today, Mr. Professor Dr. Eng Jun Kawai. Before Before that, I would like to invite Mr. Dr. Eko Hidayanto to moderate the webinar today. For Mr. Eko Hidayanto, time is yours.
Okay, thank you, Master of Ceremony, for the time. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Ohayo gozaimasu, and good afternoon, everybody. Ladies and gentlemen, first, let me confide to our teacher, our sensei, Kawai sensei. Welcome to our department, the physics department. Tiponegoro Daika Kuno, Putsuri Kaku Bu, Yokoso Kawai sensei. We are very happy that this year we can invite Prof Kawai to this lecture. As said by our department, Prof Heri, that last year we also invite Kawai sensei to this lecture with the topic about 3D printer spectrometer. But today, on this year, we invite again Professor Jun Kawai with the other topics. It's I think that is very suitable for physics department or physics student or lecturer. The topic today is about difference between heat and temperature, like this. So, ladies and gentlemen, before Kawai sensei start his lecture, let me introduce him by read his short biography. Kawai Jun, professor. He was born in Japan, 1957.
Yes.
Yes, that's right. He graduated from the University of Tokyo. As you know that Universitas Tokyo ini nomor 1 di Jepang, gitu. Ichiban Daigaku in Japan, like this. In 1982. Then he finished his master engineering at the same university from the Tokyo Daigaku in 1984. Then 1989, Kawai sensei had a doctoral degree from the same university, from the University of Tokyo. Then the work as postdoctoral from 1989 to 1993 at the Riken, Japan. Then from 1993, he moved to Kyoto University as assistant professor. So 1993, we still student in undergraduate in my university, but he already as assistant professor. From 1994 to 2001, he as associate professor at the Kyoto University also. Then from 2001 till now, he is full professor at the Department of Material Science Engineering in the Kyoto University. And I came to Kawai Laboratory since 2005. So 4 years after he got the full professor. Then this is about his research interest. His research interest is related to RF X-ray spectroscopy, then also analytical chemistry. But Kawai sensei no is interest in the toxic element analysis. He already published more than 500 paper, also several books. His index corpus about 24. And his recent activities in Kawai Laboratory as any kind of X-rays, X-ray analyzer such as total reflection, then electron probe analyzer, X-ray physics in polarized X-ray, Compton effect on X-ray fluorescence. Also, his laboratory concerned about material informatics such as Lapras and Fourier transformation, Salis entropy, still analysis, and others. Well, ladies and gentlemen, as an introduction, I will review a little bit about this lecture, like at the poster and at the flyer. You can read that this lecture will start from the difference between heat and temperature. Then similarity between the diffusion equation and Schrodinger equation is also will discuss. Then a key concept about Laplace transform also is discussed. And finally, the lecture extends to the Salis entropy of the black body radiation. It's like this. But Kawai Sensei will explain more detail in this lecture today. Ladies and gentlemen, I think the introduction is enough, and to the shorten the time. Now I would like to invite Kawai Sensei, Professor Jun Kawai, to present his lecture about difference between heat and temperature. Kawai Sensei, jikang no to syukurin o onegaishimasu, dozo. Please, Kawai Sensei.
So, thank you for nice introduction, and also thank you for inviting me again to this lecture. Can you hear me? Okay,
Yes.
my
Yes,
voice is
good.
clear. So I'd like to start my talk. Maybe it's much better to start the topic. So I'd like to share the view graph. Maybe I'm not sure. Can you see the view graph of the first page? It's the same, almost the same, but here you can find the face of Professor Eko Hidayanto. And can you see my view graph? So today's my talk is relation between heat and temperature. This is very basic for the physics, but I'd like to say from the first, have you ever checked the internet of the heat and temperature?
Yes,
or do you know something about the difference between heat and temperature? When I ask one associate professor in my department, what is the difference between heat and temperature? And then his answer was temperature. Here you can see, here is one example. Temperature is a measure of heat. So this is his answer. But today, I'd like to say this is not wrong. This is, in a sense, correct, but much more appropriate or many applications answer is maybe in this lecture, today's lecture, the relation between heat and temperature is very similar to its electric current and voltage. So the temperature is a potential, and heat is something flow from high potential to low potential. So this may be a good answer to give you many applications. So if you check the internet, another answer is heat is energy and temperature is the average speed of molecule. Then what is the relation between heat and molecule? So the temperature is cannot be defined without molecules, it's very strange. So then we have several questions, such as, is temperature related to molecule? No. We can, define the 3 Kelvin background radiation of universe. So universe is vacuum. And black body is related to the temperature and heat. And is black body related to molecule? No. And black body is can be defined for the vacuum. So this is therefore this answer is not appropriate. This answer, the molecule, so the temperature is average speed of molecule is not a good answer. And when I attended an international conference, many kinds of international conference, and during the banquet, I sometimes ask some professors from other countries, and then I ask, what is the relation between heat and temperature? So mostly their answer is temperature is a measure of heat. This is most popular answer. But the application of this definition is not so much. So I'd like to move to the more, so it's easy way to understand the heat and the temperature. So you can see here, this is the wall cross section of an house, and this is outside the house, and this is inside the house. So if the room inside the house is cooled down to the air conditioner, so the outside of the house is very hot. So the temperature distribution is just like this, and this is a good heat conductive material, and its heat conductivity is K1. And this is a poor heat conductivity, and its conductivity is K2, and its thickness is L1 and L2. So this figure is quite similar to this electric circuit. This is the electric battery, and this is these two electric resistance. So if you want to calculate the temperature between the two material here, it is T2. Then it's quite easy to calculate this resistance, electric resistance, and this resistance, and then you can find the voltage of T2 here. And then it's equivalent to the temperature here. So you can calculate quite easily using the electric circuit to calculate the temperature of two material, such as this is the wall of a house, and outside is thin but mechanically strong material, and inside is not so strong, but the heat conductivity should be low enough. So we can insulate the outside high temperature from the inside room. So I'd like to change to the Laplace transform. How many over here knows about the Laplace transform? If you know something about Laplace transformation, please raise your hand using the response. Is it possible? Maybe how many over here knows about Laplace transformation? No one? No one knows about the Laplace transformation? Is it possible to raise hand? I don't know how to raise your hands. No one knows about the Laplace transformation? Okay, if you have, I can see Eko Hidayant and Faiz Rahman here, the face. Do you know about something about Laplace transformation? No answer. Okay.
Any student can answer maybe?
No,
Okay.
no answer.
Please continue.
Okay. Okay. This is a definition of Laplace transformation. And I teach the Laplace transformation in my lecture for the undergraduate student. And I asked one associate professor. His major is it's theoretical physics, and I asked him the Laplace transformation, and I was check his lecture backside of the lecture room. Then he teach. This is the definition just like this. He taught just like this. So he wrote this equation on the blackboard, and then this is a definition of Laplace transform. So the student should, memorize this equation. And there are no meaning, no physical meaning. And this is the definition, and you must memorize. He explained in his lecture. So it's very strange. So physics should rationalize why this kind of equation is needed. And I checked the internet also. There are no page. I could not find any pages about the meaning of Laplace transform. So no one knows about the Laplace transformation. So I seek the rational meaning of the Laplace transform. And finally, I found it's not a Laplace. So I'd like to show, yes, this one. It's Heaviside. So the Laplace transform is invented by Oliver Heaviside, not by Laplace. And I check many mathematical physicist books in Japan, and their interpretation of Laplace transform is wrong. So very famous physicist wrote the book about the Laplace transform, but they start from Laplace. And no, this equation is found by Oliver Heaviside, and it's not their explanation of the Laplace transform is not correct. So that's the point. And do you know the Dirac, the relativistic, who invented the relativistic quantum mechanics? So he was his basic education was electric engineering. And he learned the Laplace transformation in his undergraduate university education. And it's a good hint for his relativistic quantum mechanics. So that means Laplace transformation is very important for the, quantum mechanics and many other physics. And so the Laplace transformation is usually used for the electrical engineering. So I'd like to explain what is the meaning of the Laplace transformation. So this is the electric circuit, just like this. Here is a electric battery, and here is a resistance, and this is inductance or coil, and this is switch. So if you close this switch, then the voltage becomes V, or I'd like to say it's 1 volt or something. Then the current here is increasing gradually, and then finally it becomes some steady state. And this current, this is current. This line curve is current, and the current is defined by the only the V and R, no relation to L. So this is maybe you know very well about the electrical or electrical engineering or something something like that. So it's quite similar to the heat transfer. So I'd like to ask you, how does change the temperature of a small matter here? This is a small matter of temperature 0 degree. And between a big and high temperature, this is a big and high temperature matter, and its temperature is 100 degree. And the low temperature matter here, it's a 0 degree. So this one and this one is the same temperature, and it is attached to the 100 degree material. Then at first, this is the temperature distribution. At first, this is 0 degree, but it becomes 100 degree. But 100 degree place is only limited here, and it's down to 0 degree. And time is longer than 100 degree is here, and then its temperature increases from 0 to some 50 degrees or something, and the temperature distribution is just like this. And here is the steady state. So here is the 100 degree, and here is 0 degree. So the temperature is linear from 100 to 0. So you now understand this curve and this curve is quite similar. So this is the current, but this is the temperature, but they are quite close relation. So I'd like to explain here how to calculate the temperature increase or current increase. So this is the electric circuit, and we apply, if this switch is closed, then it's at t equals 0. Then its voltage becomes 1, just like this. This is a Heaviside step function. It is called Heaviside step function. And maybe your physics, maybe you understand very well about the physics of electricity or magnetism and something like that. Then this is the differential equation for the capacitance. And this is a differential equation of its inductance L. So, and Oliver Heaviside thinks P equals d dt. So d dt should be expressed by P. This is a number, not the differential. So then Z equals 1 by Cp, and Z equal, this one is Z equals 1 by Cp, and this equation becomes Z equals Lp. So if you want to express this circuit by an impedance Z, then Z equals resistance and inductance. So this is the, how to say, it's the expression of the total resistance or impedance of this circuit. And Z is an current to voltage converter, and it is an operator. So if Z is operated on I, this is how to say, it's a differential operator, is applied to electric current, then we get the voltage of the this circuit. The change of current just after the switch is on is expressed as I equals 1 by R plus LP. So this one is this function. So this function is divided by R plus LP. Oliver Heaviside called this equation as algebraized. It is this equation is algebraized. Then this is in a sense differential equation or integral equation. Then if we solve this equation, we can get the its current. Okay, I'd like to move the next. So this is the denominator is R plus LP. So we must calculate this. So you know very well. So the 1 by 1 plus x equals 1 minus x plus x squared minus x, it's a cubic or something. So therefore, R1 by R plus LP equals just like this, and it is expanded to the infinite, series. Then it is just like this. Okay, and all these, calculation was done by Heaviside in 1890 or something like that, maybe more than 100 years ago. Then P is differential and P equals ddt, and 1 by P may be integral. Oliver Heaviside thought, and 1 by P multiplied the 1. This is a step function. Then the integral should be 0 to infinity, and then it becomes t. And if the p, the power of n, then it becomes just like this. This is an integral, it's a formula. Then if you want to calculate this, I equals something like that applied to the operated on 1. Then P inverse is it's integral just like this, and it becomes t and t squared, t cubic, and something. Then you can you know very well this is an exponential. This is an exponential function. Maybe you know very well. Then the differential equation zi equals 1 becomes if its solution is I equals 1 by R plus LP multiplied operated on step function, then the solution is I equals just like this. So this is the exponential function. So if the electric voltage becomes 1, then electric current becomes gradually increasing, and finally it converges to the 1 by R. So this is the solution of the it's the Lapras transformation. So you are now understanding the relation between heat and temperature is that of electric current and the voltage. And the electric resistance is an operator on current and produce voltage. So this is operator just like Hamiltonian. So it's an integral operator or a differential operator and applied on the current. And the heat is passing through a matter of thermal resistance, then temperature difference will be produced. So you can find here the temperature and heat. So heat is the the cause and the temperature is results. But we think usually the temperature is the driving force and heat is its results. But Oliver Heaviside is a very strange person. Oh, some chat is coming. Oh, okay. So the Oliver Heaviside is a very strange person, and we think usually the temperature is driving force and heat is its results. But he thinks differently. The heat is the cause and the temperature is the result. It's very strange, but the application of this way of thinking is very wide. And if the thermal resistance is zero, the heat flow does not produce temperature difference. And if the heat does not go through the material, the temperature difference is not defined. So you can now know about something about this. Okay, then we think again the steady state temperature between two matters of 100 degree and 0 degree. So big material here and 100 high temperature, and this is 0 degree large material, and this is a small material between the two. And then this is T1 100 degree, and this is T2 it's 0 degree. And the temperature distribution in the steady state becomes this kind of straight line. So you can calculate quite easily. So this is not the transient state. It's the steady state. So if you think about the thermal conductivity is K and heat flow is Q, and the temperature difference is T1 minus T2. And I'm sorry, this cross section, this square should be here. So the S is the cross section of the small material, and L is the thickness of the wall or the thickness of the material between the two big material. So you can quite easily the Q is proportional to the cross section, and its inverse proportional to the length of the material and proportional to the temperature difference. So the Q, if you write dt by dx, it's a differential type, then Q equals Ks dt dx. So something like this. And this is called Fourier's first law. I'm sorry, this is taken from my textbook, and it is, I'm sorry, it is explained by Japanese. Okay, the thermal conductivity, K. I'd like to show you some example. For copper, it's 400 watt by meter Kelvin, but copper alloy is around 100. It's smaller because of the impurity material, impurity elements. And aluminum is very high, 240, but oxide is 20, only 20. So you now understand the metal is high, and this is electric insulator is also the thermal conductivity is low. For example, iron is 80, pure iron is 80, but this is steel. It is composed of chromium 18%, nickel 8%, and the rest is iron is only 15. It's less than aluminum oxide. But you can see the diamond is 2,300. That means diamond is not electric conductive, but it's very rigid, hard material. So its vibration can be, how to say, vibration of an atom, carbon atom is transferred to the other side of the diamond solid. So graphite in plane is 1,900, but interplane is only 6. And if you want to know something about these values, the reason you must study maybe solid state physics. So I do not go further about the solid state physics. So do you know Ohm's law? So V equals IR. So how many of here knows Ohm's law? Please raise your hand. Is it possible to raise your hand or not? Maybe everyone here knows about Ohm's law. And Ohm, probably he is German, found the Ohm's law in 1830, around 1830. And Fourier published his book, 1820. That means Ohm thought the similarity between the electric circuit and thermal conductivity, and finally he found the Ohm's law. So the electric conductivity is it is written by sigma, and it's a thermal conductivity and electric conductivity are quite similar, you understand. So there are other similar laws. So Fourier's law is thermal conductivity, and Ohm's law is electric conductivity, and the Fick's law. This was found in around 1850. And this is, in a sense, it's a molecular diffusion. And how many of here knows Newton's law? Newton's law is just like this. So there are two walls in the viscous liquid, and this is stopped. And this other side of the wall is moving by the velocity of v. Then when this wall is starting, the liquid around here is moving with the velocity of v, but it dropped the speed and then stopped. Okay, I'm sorry. Then if the long enough, this wall is moving, continue moving, then this speed of viscous liquid speed here is 0, and viscous liquid here moves the speed of v. And between here, their relation is linear. And because of some fluctuation, this speed dropped. Then because of the friction, this speed becomes up. And if because of some friction, some fluctuation, this speed becomes higher than neighbors, then because of the friction, this speed becomes here. So you understand, the Newton's law is something like it's the average of the speed. Okay, then this is the cover page of the Fourier's book. So this is a French book, and this is English translation. And Lord Kelvin, it is said, he read this book by one night. Maybe you are the student in physics or mathematics. It's quite easy. So you can read one book within maybe one night, may be difficult, but within 1 week or 1 month, you can read this book. It's quite easy. Okay. Then, you know this, I'd like to move, okay. Can you see the Fick's law? Its flow is, how to say, proportional to the density gradient. And this is a continuity equation. So the density change, and this is the divergence. They are cancelled out. So if you put this J into here, then you can get diffusion equation just like this. So d rho dt equals this is read as nabla square rho. So this is another equation. This is a thermal diffusion. So thermal diffusion is quite similar, the same equation as you see. Okay, I'd like to say something about the thermal diffusion. Okay. From now, maybe the lecture becomes other complication. So I'd like to stop here, and the 20 is just the half of my lecture. So I'd like to invite your discussion or question. Is it okay, Professor Eko, Hidayanto?
Okay, thank you, Kawai Sensei. It's very nice, your lecture. Maybe our student will ask about his lecture. So please raise your hand if any question. Or you can write also in the chat room. Please, silakan kalau ada yang ingin ditanyakan. Ini yang kuliah termodinamika barangkali ya. We have thermodynamic lecture. So I think that this lecture is very appropriate with this lecture today, Kawai Sensei. Silakan kalau ada yang para mahasiswa untuk menanyakan. Have any question, please? Just a moment, Sensei. There is a question from Kitir, Mr. Kitir. Please explain again about Lapras transformation, Kawai Sensei.
Yes.
He still get the point of Lapras transformation.
Okay, Lapras transformation is very difficult. So I ask you to, can you see this page? Just wait a moment. I'd like to start again. Okay. Can you see this? So the Lapras transformation is very complicated, and I heard one researcher in one research institute, and he always have a guest of the physicist and physics or particle physicist or something. He thinks they are quite high knowledge, and always they come to his institute. He asks, what is the Lapras transformation? And no one can answer his question. So Lapras transformation is very difficult. So, and even the associate professor of my university ordered his student to memorize this equation. So it's not good. So that's the point. Lapras transformation is very difficult, but if you, read again this, and even that it may be very difficult, please find this book of Paul 9, and then you can understand what is the Laplace transformation. It may be an easy way. I'm sorry, I cannot explain. It's very difficult.
It's okay. Kitir Kung, Kitir is graduate from Kanazawa University, Kitir Binu is graduate from Kanazawa Daigaku. Okay, maybe I will ask also, it's just maybe it is a stupid question.
Okay, I will start. If I will start, maybe okay.
Okay, I will ask later.
Okay, I will start. Something wrong, I'm sure. Okay, I will start. Okay, can you see the view graph 20?
Yes.
Okay.
Yes.
So this is the diffusion equation. So if we put dx replaced by delta x, and this is a finite interval. This is infinitely small interval, and this is dt is infinitely small time difference, but we use delta t. So they will be, I'd like to say, so the delta x equals 5 centimeter, for example, and delta t equals 83 seconds. So even such rough it's quite good. Okay, then so the left hand side over here is dt by small dt equals just like this. If we replace the dx by delta x and dt by delta t, and right hand side is it's a 2 orders differential, and then it becomes just like this, and then tx plus delta x minus tx minus delta x divided by delta x. So the right hand side becomes just like this, and we put the left hand side equals right hand side, then it becomes just like this, and then we found here is alpha, and we found if this is common to this place and this place, and this, if this is 2, this equation becomes very simple. So if we put this as 2, then t plus delta t, this is here. So the temperature at t plus delta t, it's delta t future is equals to x tx plus delta t and tx minus delta t. It's averaged. So this is the this temperature is here, here, and this temperature is here, and it is divided by 2. The average is here. So if you draw the line of two points, and this is the average. So at first, time t, the temperature distribution is just like this, but it becomes here. So this is a diffusion equation. So diffusion is averaging, you understand. So this is very important. So that I'd like to solve one problem. So there are 2 iron slabs, just like this. This is 20 centimeter, here and here. And this slab is 100 degree, and this slab is 0 degree. So at t equals 0, we attach 2 slabs, and it's adhered quite strongly. Then outside of this 100 degree slab and this outside of this 100 degree, 0 degree slab, should be cooled down to 0 degree. So how is the temperature distribution inside after 10 minutes? So after 10 minutes, we divide it by delta X equals 5 centimeter. Then this is the one, this is here. So you can see here the delta T equals 83 seconds. Then about 10 minutes is 7 delta T. So we repeat the averaging just like this for 7 times. Then the 7 delta T, the temperature inside the iron slab becomes just like this. So I will show you. So at first, so the time 0, this is 100 degree, and this slab is 0 degree, and outside is 0 degree, and this outside is 0 degree. Then, so this point should be 0 degree, and here is 100, and this is 100 and 0 degree, and it is averaged just like this. And then this point is, so they should be averaged to here, and this should be averaged to here, and this temperature should average to here. And then this point should be averaged to here, and this point should be averaged to here. So the temperature becomes just like this, and then it becomes just like this, and then finally the temperature becomes just like this. So you can quite easily calculate the temperature inside the iron slab, and this temperature distribution is quite reasonable. Okay, so I'd like to move. So you now understand diffusion is average. Okay, you understand a very important thing, that diffusion is average. Then how is the relation, Schrodinger equation and the diffusion equation? So it becomes a little bit difficult, but it becomes. So this is a Schrodinger equation of no potential energy. That means electron is moving in a space of the vacuum, and then without the neighbors of the electron, no stars, and that means it's a free traveling electron. Schrodinger equation is just like this, and this is the diffusion equation. If you compare these two equations, this Schrodinger equation can be transformed just like this. So this alpha, diffusion constant is this one, and so the time differentiation is not the time, it's IT, it's an imaginary time. So the Schrodinger equation is a diffusion equation of imaginary time. This is maybe you know already knows if you run the quantum physics. So, what is the voltage and what is current of this Schrodinger equation? So I do not give you the answer, and you can think by yourself. But so if here is imaginary number here, this is not the true diffusion equation. It becomes a wave equation, just like this. This is the at time t equals 0, the particle is on the origin of the in the universe. Then it moving it start moving with the velocity t, velocity of v. Then it moved to this way, and its wave function becomes like that. And its wave function after t equal 10, the wave function becomes just like this. I'm sorry, this is taken from my Japanese paper, and it is written by Japanese. I'm sorry. And this is the diffusion equation solution. Okay, I will explain this afterwards. So this is the diffusion equation. So do you know Green's function? Green's function is defined as the system. This is a differential equation or any kinds of system that if you put into the system the delta function, then its output is Green's function. This is the definition of Green's function. So I'd like to show you a very easy example. So here is an iron rod, iron bar here. And one cross section is evaporated, the chromium thin film. And then another iron rod is welded to this first iron rod. And then here is the chromium thin film. And this looks like a delta function. And if it is heated, then this chromium atom distribution becomes Gaussian function just like this. And its concentration is, this is a Gaussian function. So this is the Green's function of the system of the diffusion equation. Okay. I'd like to move. Okay, maybe it's much better to the full screen mode. Maybe this is okay. Then this is the delta function is put into the diffusion equation. Then you get Green's function, and the Green's function of the Green diffusion. The Green function of the diffusion equation is Gaussian. So this is the Gaussian. So the atom will be diffused just like this. Okay, maybe it's easy to use just like this. Maybe this is much better for me. Okay, I'm sorry. If you want a Green's function of Schrodinger equation, you can easily estimate it by comparing two differential equations of the diffusion equation and the Schrodinger equation. So this is the Green's function of the Schrodinger equation. If you know of diffusion, you can feel the wave function. This is a wave function, and so you can calculate the wave function or Green's function of the Schrodinger equation. It's quite easy to find it's very complicated calculation, but you can feel the wave function because heat is quite easily understandable by instinct. So, and again, if you put T here, is replaced by minus I beta H, and this is a Planck constant divided by 2 pi. And where beta is 1 by kT, it's an inverse temperature. Then the new equation becomes an equation of quantum statistical mechanics. So you can proceed your wave of your instinct. How to say, this is a Schrodinger equation and the quantum statistical mechanics. So if you want to know about this, you can check the textbook of Feynman's statistical mechanics, the textbook, or path integral textbook. Okay, so I'd like to return to the Laplace transform. And so the Laplace transform was originated from Laplace probability theory. So the Laplace published early 1810 or 20, the theory analytic de probabilité. So if you read this textbook can be found in the internet. It's a scanned textbook you can find in the internet. But if you check this textbook, no Laplace transform equations are here. It's a completely different way of writing, way of expression. But Heaviside, about 100 years after of Laplace, this book, independently began to algebraize the differential equation, and around 1890, and as a response to the step function. So if you want to understand the Laplace transform, you must run the algebraize of the Heaviside way. So I have talked about the quantum statistical mechanics. So you know the microcanonical ensemble and canonical ensemble and grand canonical ensembles. So these are the essence of the statistical mechanics. And if we express the microcanonical ensemble as WE, then the canonical ensemble is a Laplace transform of microcanonical ensemble. And the grand canonical ensemble is again the Laplace transform of the canonical ensemble. This is a Gibbs distribution. So the Laplace transform is very close relation to the many area of physics. And its meaning is very difficult to understand, because most of the textbook of Laplace transform is originated starting from the Laplace, but it's completely different. You must start from the Heaviside textbook, but Heaviside was not educated person. His papers are very difficult because he only went to maybe elementary school or junior high school, and he did not graduated the university. So he published many papers, but they are very difficult to understand. Okay, and I will change to another topic. So the radiation heat transfer is again, it's similar to the electric circuit. So this is a gray body. The black body is it's an ideal black body, but the real body is usually gray body, and the two gray bodies are here, and so the one gray body emits the heat radiation, and it is absorbed, and also it radiates heat again, and it is absorbed by the first gray body, and again it's emit the heat, and so on. So this temperature is T1, and this temperature is T2. So the temperature is here V1 and V2, and the gray body effect is it's an internal resistance of the electric battery, and this geometric factor is expressed by this resistance. So again, I do not go into the details, but the radiation heat transfer is again, excuse me, again, you can interpret by the electric circuit, just like this. Okay, what is black body radiation? So the Planck formulated the black body radiation, and this is the Planck's equation. I omitted here the d lambda and here the d lambda. So this is an electric furnace, and it is heated up to 1000 degrees or something like that. And a small pinhole can emit the intensity distribution is measured by the thermocouple. Then you can find the Planck found the equation just like this. This is a black body radiation. And here it's a, you can treat the boson ideal gas or photons ideal gas, not the molecule. It's it should be vacuum is okay. So the boson or a photon inside is it's equilibrium ideal gas, and it emits heat radiation, and this is a black body radiation. So I'd like to talk about the Tsaris. So he is Professor Tsaris. I visited his lab, his office, about 10 years ago in Rio de Janeiro, in Brazil. And so Tsaris proposed the exponential function should be replaced by this equation. And here it's a Q. And if Q equals 1, then it's exactly the same expression as this becomes exponential. But if Q is different from 1, there are some physical meaning. And it is said it's a Q statistics. And so you find here, this is exponential. So this exponential is replaced by this expression. Then you can express many things, such as synchrotron radiation. And synchrotron radiation is a kind of black body radiation. And so this is the cover page of my paper, and the similarity between black body and the synchrotron radiation analyzed by Tsaris entropy. I'm sorry, this is Japanese. So if Q becomes 1, this expression becomes exponential. So the synchrotron radiation is just like this function. It's just like this, and the black body is just like this. But if Q equals 1.05, then almost their line shape is quite similar for intensity at the order of 15, and this photon energy of the order of 15th. Their matching is extremely. And so this is completely advanced research, but you can now understand, you can know something about the Tsaris entropy. It is different from the Gibbs entropy, but something advanced physics. Okay, the homework, you can bring these 1, 2, 3, 4, 5, 6 points to your home, I think. This is a summary of my talk. It's that slide number is 40. This is the last. So the relation between heat and the temperature is quite similar to current and the voltage. And you understand now the relation between Schrodinger equation and the diffusion equation. And the diffusion is, in other words, it's averaging. And you know now the Laplace transform is a response to the step function. And impedance, Z, is an operator on heat or on current to yield the temperature or voltage. The temperature or voltage is the potential. And the current or voltage relation exists everywhere. For example, the money and the richness. So the money is current and the richness is the potential. But in this case, the money moves from poor to rich, and the richer people becomes much richer. But if you find some physics, then you can make a good proposal for the averaging of the poor and the rich. Then it may be a good thing for the poor people. And also DNA. Your DNA will be distributed by your children, and in the future, your DNA is diluted, but average and expanded to this world in the future. So thank you for your attention. This is the last of my presentation. Thank you very much. So I'd like to stop okay.
For this lecture, it's very interesting. There are some questions from student or lecturer. One question from Sarif Hidayat. Maybe he is student in the physics. His question is about increasing heat flows. How about increasing heat flows, Kawai Sensei? Is it important to thicken walls or areas? Maybe in Japanese, KPO, Atsuru.
I cannot understand your question.
How about increasing heat flows? Is it important to thicken walls or areas? Maybe, KBO Atsuku Suru.
Yes, if the wall thickness becomes thin, so its K, the thermal conductivity increases, and its cross-section surface area becomes wider. Then the heat flow becomes large. It's quite easy to understand from the expression of the heat.
Okay, Sarif Hidayat, bagaimana? Sarif Hidayat, do you understand? Okay, okay. Then again,
of course. Thank you, Prof, from the answer.
Okay.
Okay, okay. Now the question from Professor Vidayat. He is from chemical engineering. When we use Laplace transformation, separation or combination variable in PDE solution is something confused. He is confused to teach in this method. When he using Laplace transformation, Kawai Sensei. Separation or combination?
That means partial differential equation. So this is a question about the partial differential equation.
Yes.
So if you use the diffusion, if you use Laplace transformation to solve the diffusion equation, so its solution is in a sense it's expanded by the error function. So the error function has x and t. That means the variable is not separated. So if you use the Laplace transformation, you don't need to separate the variables. It's quite complicated. But if you use Fourier expansion to solve the diffusion equation, you must separate the variables as t and x. The time and its position should be separated into two ordinary differential equations. So this is my answer. Okay.
Okay, thank you, Dr. Eka, for Professor Kawai for answer.
You are welcome.
To answer our student in our lecturing in mathematics for chemical engineering. Thank you, Professor.
You're welcome.
You're welcome.
Oke, ada pertanyaan yang lain? Any other question, please? Silakan bisa, you can directly ask to Kawai Sensei. Raise your hands, please. Silakan. No, ada? Silakan.
No questions?
No question again?
You are so shy.
Okay, maybe
usually I ask a question in the international conference about maybe 200, 300 researchers, and I ask quite a stupid question every time. So
I also ask a stupid question to you, Kawai Sensei.
No problem.
If someone is contaminated with COVID-19, like in the years or last year, it's infected by another person, can the heat transfer from other to another is calculated by Laplace or Laplace question or other questions such as fix or another? How opinion about it?
It's a kind of the diffusion.
Yes,
it's some problem of diffusions, and you must simplify the problem. It's very difficult.
Yeah, it's masuk kasih.
Yeah, it's very difficult to simplify the problem.
Okay, there is any question from again, second question from Kitaribinu Sensei. Is there any relation Fourier transformation with Laplace transformation? Is Laplace transformation is the generalization? Is the generalization, Kawai Sensei?
Yes, some people say the Fourier transform is it's more basic, and because its variable is from minus infinity to plus infinity, and Laplace transform is its integral region is from 0 to plus infinity. So the Laplace transformation is much advanced, and Fourier transform is much basic, some people say. But I think they are very different. So that means Fourier transform, for example, if you use Fourier transform to solve the diffusion equation, then its basis function is sine and cosine and exponential functions. It's exponentially, it's a time function of exponential, and it's a position function of sine and cosine. But if you use Laplace transformation to solve the diffusion equation, its solution is the infinite series of error function. And error function contains both position x and time t. So it's maybe completely different. But Laplace transform, it's very important. Laplace transformation is not invented by Laplace himself. It is invented by Heaviside. So this is the point. Okay.
How about Kitir Binu, Kitir Sensei? Bagaimana? Is it okay? I think it's okay, Kawai Sensei.
Oh, thank you.
Maybe there is okay. Is it okay?
Yeah.
Ada yang lain? Any other question, please? Silakan, bisa tanya langsung, bisa. Oh, there is also from Kiterbinu. Is there any physical meaning of imaginary time in diffusion equation?
I don't know. I don't know its physical meaning. Maybe it's only the formal expression, and so no real physics about the imaginary time. I'm not sure. So you maybe find the physical meaning of imaginary time in the future.
SKW Sensei know that Kiterbinu is a student in Kanazawa University. He takes physical theory. Oke, ada yang lain silakan. Kalau masih ada.
23 to 29 slide. Explain again about the slide. Shall I explain again?
Yes. Yes, Sensei.
Okay.
Yes,
okay.
Sensei.
Okay. I will try.
What's the meaning? What's the meaning? The color line, Sensei.
Pardon? What's the meaning of
color line? Color line in slide.
Okay. I will explain. So can you see this slide? Diffusion is averaging.
Yes, Sensei.
So this is the first temperature distribution, and then next this how to say something abnormal temperature. It's not averaging temperature. It should be averaged to here. So one slab is 100 degree and the other slab is 0 degree. So here you can see here this is the 0 degree and 100 degree and 0 degree. So next 83 seconds, then this temperature becomes this temperature, and this temperature does not change because its average is the same. And this temperature becomes just like this, and this temperature does not change because the average is the same. And then next 83 seconds, it becomes this just like this. So this is how to say it's this point should be averaged to here, and this point should be averaged to here, and this point should be averaged to here. But this point is the average of this and this is the same. So the temperature does not change here, and so on. So you can see here I don't know how to say echo Do you know the words Japanese tongari, tongari,
Kongari.
tongari,
I
tongari,
forget.
tongatteru. So that
What kind
this is tongari.
Triangle maybe.
Yeah, something it's a skew or something it's I don't know how to say in English. But this kind of high temperature or low temperature place becomes its average between two, average between the neighbors. So this is the diffusion equation. I'm sorry, I cannot remember I don't know the English words. Okay?
Okay. Arigatou gozaimasu, Sensei.
You are welcome.
Once again, a question from Nixon Kenny. If heat temperature is analogs to the current and voltage, can we solve the heat problem with the electronic approach and vice versa? Or are there any condition where this definition is violated?
Yes.
This question like this.
Yes. It's quite easy to calculate the electric circuit, and sometimes the heat transport is very difficult. So you can calculate the electric circuit, then it is moved to the heat temperature relation. And usually we perform this kind of calculation, and also the diffusion equation of the concentration is also quite similar. So electric circuit is always quite simple because it is ideal electric circuit. So it's true. Your question is quite good. Okay.
It's good. Nixon Kenny, it's okay. Okay. Maybe there is a question again. One or two question is okay, I think. But if there's no question, I will wait till 1 minute.
I have used the PDF file of presentation number 7. So I will send this PDF file to Eko Hidayanto afterwards.
Okay.
Then you can distribute to any students.
Okay.
Yeah. And all the figures, only one exception is maybe one exception is this photo of the cover page of this book, and maybe this cover page, and the others are all by myself, and it's okay to distribute. Maybe the cover page is no problem, I think. You can distribute. This is the book of Kyoto University. So if you come to Kyoto University, you can read. But maybe this is not so special. So you can find in Indonesia, and many kinds of free books you can find in the internet. So this is already the copyright has been expired, and scanned book you can find in the internet.
Okay, everybody, is it okay? Maybe I will summarize Kawai Sensei lecture today, but I just read from Kawai Sensei PPT that there is a relation between heat and transfer, such as current and voltage. Then the second one, just a moment. The diffusion is averaging like this. The third, that Lapras transform is respond to the step function. Okay. Then the impedance is operator on heat, such as current, to yield the temperature or voltage. Then the last one, current and voltage relation exists everywhere, such as money and richness. Okay. Kyomi bukai for sentence, Kawai sensei. Kontoni, arigatou gozaimasu. Ladies and gentlemen, the Kawai sensei has already finished his presentation. Then, okay, thanks for your kindly attention. But after this session, MC will ask to Kawai sensei to receive any certificate from our department. So, Mr. Ceremony, time is yours. Silakan, MC.
Thank you very much, Mr. Professor Kawai, for wonderful presentation and explanation about difference between heat and temperature. Hopefully, it can be useful for us.
So, hello. Thanks to Mr. Eko Hidayanto, who has moderated this webinar today, so it can run smoothly.
Ladies and gentlemen, we would like to give an appreciation for Professor Kawai. It's been a certificate. This is certificate to Mr. Kawai. Thank you very much, and we wish you more success in the future.
Okay, Kawai sensei, this is just a certificate from us. Worthless, I think. But I hope you can accept it. I really thanks to your knowledge transfer today to us. Kontoni, arigatou gozaimasu. Thank you very much from us.
Shukran.
Again, on behalf of our department, I officially close this general lecture. Again, we will thank to Kawai sensei for the sharing of his knowledge. I hope this the lecture is very useful from us and my student. I close this lecture by say an Islamic hamdalah. Alhamdulillahirabbil alamin.
Alhamdulillahirabbil alamin.
Again, thank you, Kawai sensei.
Thank you very much, Kawai sensei.
Thank you very much, Kawai sensei. Nice to meet you next time.
Terima kasih Bapak Ibu dosen dan peserta yang sudah berkenan hadir pada acara sore hari ini. Thank you.
Terima kasih Mas Ocha.
Terima kasih Pak Zainul.
Terima kasih. Izin keluar Zoom.
Oke.
Monggo.